Today we are looking at one of the most important machines in the electric grid, the utility-scale synchronous generator. In a thermal plant, steam or gas turbines spin it. In a hydro plant, water turbines do the same job at a different speed and geometry. Either way, the generator converts mechanical shaft power into large-scale electrical energy with very high efficiency. The machine looks simple from the outside, but inside it is a carefully balanced system of steel, copper, insulation, cooling, excitation, protection, and control. The big question is not just how it makes electricity. It is how it stays synchronized, stable, cool, and reliable while feeding thousands or millions of customers. At the heart of the machine is Faraday's law. A changing magnetic field induces voltage in a conductor. In a synchronous generator, the rotor is an electromagnet supplied with direct current, creating north and south magnetic poles. As the turbine turns the rotor, its magnetic field sweeps past the stationary stator windings. Those stator coils are physically spaced 120 electrical degrees apart, so the induced voltages are also 120 degrees apart. That gives us balanced three-phase alternating current, phase A, phase B, and phase C. When the rotor speed, number of poles, and grid frequency line up, the machine is locked in synchronism with the power system. Mechanically, utility generators are built around stiffness, insulation, magnetic performance, and heat removal. The stator frame holds a laminated silicon steel core that reduces eddy current losses. Heavy insulated copper bars or windings carry enormous current, so their insulation system is a major reliability boundary. Rotor design depends on speed. Steam, gas, and nuclear units usually use long cylindrical rotors designed for high speed and high mechanical stress. Hydro units often use larger salient pole rotors because they run more slowly and need more poles. Around this core system are brushless exciters retaining rings, bearings, seals, hydrogen gas recirculation, and in large machines, direct stator water cooling to remove heat where it is created. Control is what turns a powerful rotating machine into a grid asset. The automatic voltage regulator, or AVR, adjusts the rotor's DC field current. More field current increases magnetic flux, which raises terminal voltage and changes reactive power output. Less field current does the opposite. Meanwhile, the turbine governor controls mechanical input power. That primarily changes megawatt output and helps maintain speed. Synchronous speed is set by the formula N sub S equals 120 times frequency divided by the number of poles. For a connected generator, frequency is tied to grid speed, so operators manage real power, reactive power, voltage, and stability as one connected system, not as separate knobs. If you are operating or maintaining a high voltage generator, here are 5 non-negotiable guidelines to preserve machine health and avoid catastrophic failure. First, monitor stator and bearing temperatures continuously using embedded RTDs because thermal expansion stress is a major cause of stator winding insulation breakdown. Second, maintain hydrogen purity and pressure on hydrogen-cooled units, keeping purity strictly in the safe operating range to avoid dangerous air-hydrogen mixtures and preserve cooling efficiency. Third, track shaft vibration trends with proximity probes on journal bearings because sudden spikes can indicate rotor unbalance, thermal bowing, or bearing oil whip. Fourth, perform regular insulation resistance and partial discharge testing to catch microscopic void breakdowns before a phase-to-ground fault occurs. And fifth, inspect the excitation system, rotating diode bridges, and AVR response during load swings so the generator can recover quickly from disturbances. So a utility-scale synchronous generator is much more than a spinning magnet. It is a workhorse that combines mechanical engineering, electromagnetic physics, thermal management, insulation science, and real-time control. The turbine supplies torque. The rotor supplies magnetic field. The stator delivers three-phase power. The AVR shapes voltage and reactive power. The governor manages real power and speed, and the operator keeps the whole system inside safe electrical, thermal, and mechanical limits. When all of that works together, one machine can support an entire region of the grid. If this breakdown helped, Like the video, subscribe, and join me for the next engineering deep dive.